Hello, my name is Wilbert Andres Ruperto Hernandez, and I'm the project leader of the Exploration Multi-Purpose Rover for Expanding Surface Science, EMPRESS, from the University of Puerto Rico at Mayagüez. In this presentation, you will learn about the project development timeline, the lunar surface concept of operations, the engineering design and analysis, and the cost and risk assessments of our project. EMPRESS will support NASA's Artemis program when it lands at the south pole of the moon in 2023, in preparations for the Artemis 3 mission in 2024, which will land the first woman and the next man on the lunar surface. The rover has 3 operational modes: autonomous, teleoperated, and crewed. In these configurations, it will enable high-priority science research, risk reduction activities, technology demonstrations, payload transport and delivery, among other activities. It has been designed with human spaceflight standards and considerations, and innovative technologies that will enable it to expand the range of robotic and human exploration of the moon. The project complies with the following requirements set by the competition. The rover operates robotically for 1 year until the crew arrives. Once the crew of 2 astronauts arrive, they will reconfigure their rover for their use as an unpressurized surface mobility system during their 6 to 6.5 day surface stay. The mass of the rover is limited at 300 kilograms and the cost is limited at $300 million. Taking into consideration the complex and challenging deadline for this project, we have made the following assumptions. The first assumption is that the project will follow a multi-center approach led by NASA's Johnson Space Center due to their expertise in human spaceflight, while the NASA Jet Propulsion Laboratory will design the vehicle due to their expertise in planetary exploration rovers. The Glenn Research Center will support the full-scale environmental test and the development of the National tire. Kennedy Space Center and Goddard Space Flight Center will support the design and implementation of the lunar dust protection systems. The integration and launch of the rover will happen at Kennedy Space Center in conjunction with a commercial partner. Marshall Space Flight Center will support the design of the rover and make sure that it is compatible with a commercial lunar payload services lander that will take it to the moon.
The scientific objectives selected for EMPRESS were based on 8 concepts outlined by the Committee on the Scientific Context for Exploration of the Moon. Data recovered from the instrument on EMPRESS will help study the bombardment history of the inner solar system, the structure and composition of the lunar interior, the diversity of crustal rocks to understand planetary processes, and volatiles in the lunar polar region.
Also, the lunar volcanism and compositional evolution of the moon, the impact processes on planetary scales on the moon, the regolith and weathering processes on Mayagüez airless bodies, and the processes involved with the atmosphere and the dust in the environment of the moon. The surface operation of EMPRESS are subject to the continuation of the Artemis missions and the need to use a rover for crew mobility. In order to map the routes for EMPRESS, we assume 2 things. The first one, we assume that the Artemis mission will be 3rd year since 2024. And we also assume the landing sites of those missions based on geological features and also scientific interest of different places around the south pole of the moon. With that being said, the goals for EMPRESS are: in 2023, EMPRESS will be landing at Shackleton Crater. In 2024, the Artemis 3 mission will be landing at Shackleton Crater. In 2025, the Artemis 4 mission will be landing at Slater Crater.
By 2026, Artemis 5 will be studying the surroundings of Shoemaker. Then by 2027, Artemis 6 will be studying the surroundings of Faustini. Then by 2028, Artemis 7 will be studying the Amundsen crater.
The selection of instruments chosen to be part of the rover was based on their ability to collect the data needed to address the scientific objective of EMPRESS, their technology readiness level, and their heritage from past robotic missions. We have the NSS, that is the neutron spectrometer subsystem, and this instrument measures the change in the number and energy of neutrons coming out of the regolith. We have the NIRVSS, that is the near-infrared volocule spectrometer subsystem, and NIRVSS will help us to identify surface and near-subsurface volatiles. NSS and NIRVSS will be also flying in the volatiles investigating Polar Exploration Rover, also known as VIPER. After talking to Mr. Daniel Andrews, who is the project manager of VIPER, the team decided that EMPRESS can support VIPER's scientific objectives, since it will be operating for a longer time and it will be visiting different places of interest. We also have PIXL. PIXL is the planetary instrument for X-ray lithochemistry, and PIXL will help us to identify chemical compounds on the lunar rocks.
The rover will include two MASCOM-Cs, which helps to provide a full description of the topography, geomorphology, and geologic setting with the help of an iterative closest point algorithm. Both MASCAMs will gather a series of data points, preferably the moving in the process, to create multiple data clouds with different angles. The series of data points will be stored and then matched with the closest point in the reference cloud. Afterwards, each source point will be aligned to its match found in the previous stage. Then transform the source points using the obtained transformation. Finally, it will use the iterative method and get the resultant matrix. The NAVCAMs will help with the rover operation and hazard avoidance. To give the MASCAM-Cs and the NAVCAMs the ability to take pictures in high contrast and low luminosity conditions of the lunar surface due to the low solar elevation angle, the cameras will have the implementation of an ITEM-CCD, which combines the technology from interline transfer CCDs and electron multiplication technology.
The VEGA instrument is a gravimeter and will help us to understand the density variation in the subsurface. On the other hand, the RAC, or Regolith Adherence Characterization Instrument, will help us to understand the processes related to the lunar regolith. The instrument was announced as a lunar payload last June. On EMPRESS, it will be located in the robotic arm because the arm will be in constant interaction with the lunar surface.
Starting off with the design overview, on the left, you can see the mass distribution table. On this table, we specify the mass of every component of the vehicle and achieve a total mass of 290.25 kilograms. On the right side, you can see the dimensions of the vehicle. We have a max width of 3.24 meters, a max height of 4 meters, and a max length of 3.85 meters. On this slide, you can see how the rover deployment will function. On the image on the left, you can see when the rover is still on the lander. On the image of the center, you can see when the rover is off the lander but not deployed. And on the image on the right, you can see when the rover is fully deployed and operational. Understanding the operations and results of the LRV wheels and how they exhibited mechanical failures, we looked for different options. We found out that the Nitro tire, which is currently under development at Glen Research Center, is the most advanced tire at the moment. This tire can endure extreme deformations without suffering mechanical failures. It can also prevent vibrations that are dangerous for the rover and the crew. These vibrations are commonly present on rovers that use aluminum tires. After consulting with Dr. Santo Badura, lead of the Glen Research Center Nitro Tire team, it was determined that this tire needs an accelerated timeline development and resources to meet the deadline. Most importantly, this tire needs certain modifications to allow it to sustain the loads, deformations, and temperature changes that it will be exposed to.
After studying different types of suspension system, the double wishbone coilover with a permanent magnet arrangement proved to be the best option. The deciding factor was that it provides better damping effectiveness than a fluid-based coilover. An advantage of the double wishbone is that it can handle large deflection and load due to the vertical displacement of the wheel. Components, including rubber bushings and steel sleeves, were designed with consideration for weight reduction and better performance. The suspension system is the same in both front and rear sides due to the Ackerman four-wheel steering that the vehicle possesses. For redundancy purposes, the two rear steering attachments were adapted as an emergency brake. The emergency brake consists of a two-link mechanism that holds a semi-metallic brake pad, reassembling a drum brake. Each tire will include two of these mechanisms to ensure a proper brake.
The rover frame design is a tubular chassis structure combined with multiple honeycomb platings. The tubular chassis gives the frame mechanical strength to forces from any direction, while the honeycomb platings provide a low mass flooring to the sections of the frame that need it. The frame is composed of T300 carbon fiber, primarily due to its low density and high yield strength. The frame also features attachment points for instruments such as the mass cam and the drill for easier integration of these instruments to the chassis. The front of the rover is covered with multi-layer insulation to protect essential components from the extreme temperatures of the moon and to prevent lunar dust from entering this section.
The finite element analysis was used to ensure the feasibility of the chosen design and its resistance to the expected loads. The estimated total of the expected forces acting on the frame in a current configuration is approximately 2,227 newtons. This force applied to the frame considered the weight of both astronauts on the moon, which is estimated at about 874.6 newtons. This includes the mass of the astronauts as well as the mass of the XEMU spacesuit. The total force also includes the solar panel assembly, which is expected to be around 27 newtons, and the expected normal force that the rover will exert through the suspension system, which is expected to be 1,300 newtons at a 68-degree angle. At this nominal state, the stress received by the frame was between 2.83 and 3.77 megapascals and was distributed throughout the joints of the tubular frame and where the seats will be located. The frame's deformation was minimal, having a maximum resultant displacement of 0.0519 millimeters in the area between the seats and the solar panel. To further verify the design's performance, the design was submitted under other unexpected forces, in which the suspension forces were ranging between 1,500 to 2,500 newtons, taking into consideration unexpected bumps or shocks. As a result, the further the forces increased, the stress also increased proportionally in expected areas, while strain and displacement decreased once the forces surpassed 2,000 newtons, suggesting that as the forces increase and start to compress the frame, the tubular design distributes the force more effectively throughout the whole body.
One of the main hazards for both the astronauts and the rover is the presence of the lunar regolith dust. It can damage and compromise the joints on the rover, and it can be a serious health hazard to the astronauts should they inhale it or should their suits come in contact with it, as it can severely damage the suit's integrity. To combat this issue, the team has decided to implement 3 measures onto the rover: the beta cloth for the major exposed joints, such as the robotic arms, the solar panel base, the mass cam, and the suspensions, as can be seen in the images to the right. The optodynamic dust shields, or EDS, for the solar panel cells, as they are lightweight, transparent, and self-cleaning. Finally, Nolus coating was utilized for the protection of the more exposed areas on the rover. Through use of these 3 measures, the rover will be protected from the lunar regolith dust, but will not be heavily hampered by the mass of these implementations.
For the passive thermal control system, we have a heat sink with a phase changing material, in this case phosphate chloride. With his melting point will help us to keep the component temperature around 28 Celsius degrees. The TCS also have round fillets to dissipate the heat more uniformly to the PCM. I have a fully melting PCM. The cryogenic heat pipe will help to make a quicker transfer and avoid the freezing in the working fluids of the heat pipes. The TCS have a total storage capacity of 3,012 kilojoules. I will cover a surface area of 38 meters squares. At the time that we worked, it was 1.5 hours. Of course, these numbers are approximation because we exaggerate a little bit the calculation to have a redundancy system just in case one of the system broke or prevent the overheating of the system. In the left, we see the TCS components and the front of the vehicle with his radiator.
Force analysis in this case was calculated as the necessary force to produce a net force of 0. This net force allows for a constant velocity during the trip. Using 4 motors with 1.26 Newton meters of torque, the max angle using a gear reduction of 40:1 is 14.87 degrees. Meanwhile, the minimum angle is 6.79 degrees using a gear reduction of 20:1.
The rover has been designed with detachable and replaceable components that maximize the use of space and expand the types of missions and tasks that the rover can complete. It also facilitates the crew-rover interaction. An example of the modularity is the storage compartment, which can be used to carry geological tools, instrumentations, and rock samples during the extravehicular activities. 2 of these compartments will be positioned behind the seats, as seen in the image. If additional storage compartments are needed, they could be positioned under the seats and on the backside of the vehicle. Another example of modularity is the sample return system, which will be explained in the following slides.
The rover will have the capacity to carry 4 types of payloads in the payloads attachment system, these being deployable passive, deployable active, static passive, and static active. The payloads that are deployable will be deployed either by humans or by the robotic arm. These payloads could be from NASA, academic institutions, or international and commercial partners. The mechanical interface is a bracket system that was designed in such a way so it is available in different sizes and shapes in order for the payloads attachment system to hold different payloads on its plate. Each of these payloads will have a thermal, power, electrical, and communications interfaces that, though not defined, are compatible with the rover so that they can be detached from the rover and replaced by other payloads in case they were to break during the mission. Additionally, 10 kilograms were reserved from the total mass of the rover to be used for payloads.
For the robotic systems and surface operations of the rover, an instrument and payload manipulation device and coordinating device were added to the vehicle. These robotic arms can conduct surface science experiments, sample gathering, and instrument and payload manipulation. The IPMD holds the PIXL and is capable of manipulating payloads like rack and interchangeable end effectors like scoop or robotic twister. The IPMD located at the front of the rover reaches up to 1.52 meters by using 5 brushless DC motors to provide robotic movement. On the back of the rover, the CDD will reach up to 1.22 meters with 4 BDC motors and a percussion drill capable of gathering 6 square samples up to 24 centimeters in depth and 4 centimeters in diameter. These samples will be stored in a detachable sample return system that have been designed so that the astronaut can remove and replace them for further missions.
The EPMD maximizes the use of this rover during its robotic operational mode. This robotic arm can employ different tools to conduct surface science and to deploy payloads, cargo, and surface assets in strategic places on the lunar surface. In the case that the rover is no longer required as cruise surface mobility, it could provide cargo transport and delivery for the remainder of its lifetime.
In terms of the rover-human interface, the vehicle is designed to comply with all the necessities that an astronaut needs to be able to successfully fulfill the mission. As observed in the image at the right, it has a seat with a stand at the back to hold up the life support, diminishing any potential back problems that the astronaut could experience as a consequence of the exposure to 1/6 of gravity. Moreover, the control system is composed of a joystick that provides accessible controlling movements to easily drive the vehicle throughout the lunar surface. And this system also has a display that considers eye health to provide a better visual experience, which will be discussed later in detail. Furthermore, the seats have a seat belt made of thermal micromeroid garment that supports the astronaut during the activity, providing a safe work environment. And it also has a handle that will help to facilitate the ingress and egress of the astronaut to the vehicle.
Anthropometric and biomechanics for the design data for seating were conducted by utilizing the NASA SED-3000 Volume 1 Section 3.3. Within this, the measurements were based to approximate XEMU spatial dimensions, thus applying the 5th percentile of an American female and the 95th percentile of an American male for calculating average seat dimensions. Dimensional data used for seating considerations were the following displayed. The portable life support system resting stand measurements were calculated using Hamilton standard dimensions for adequate PLSS placement. Furthermore, the standard EVA handhold dimensional requirements from NASA SED-3000 14.5 EVA mobility and translation were implemented. Moreover, the exhibited rule assessment worksheet evaluation yield a score of 2, thus indicating that the astronaut is not exposed to ergonomic risk factors related to upper extremity musculoskeletal disorders or MSDs. Such analysis was determined to assess a cautious posture.
The lunar rover was designed strategically to facilitate the ingress and egress motions for the astronauts. To demonstrate, the rover's frame is at an ergonomically favorable height, so the astronauts' efforts do not have to go beyond the aid provided by the 16G. Even more, the handle on the seat provides support during the process, hence facilitating the astronaut's capability of extravehicular activity. The rover's interior design was also considered for the ease of motion, as all components of the rover's interior are spaced in such a way that provide the astronaut with enough spacing for movement. It also allows for convenient motions during rover and crew interactions.
For the design of the display, there were certain factors and variables taken into consideration, such as ergonomics, brightness, eye health, simplicity of symbols, and electroencephalography response. The balanced combination between the colors and illumination of the icons can represent a better and faster EEG response. If the crew vitals drop below average levels, the emergency evacuation mode will be activated to safeguard the life of the astronaut by returning the crew back to the lander.
The display will also have adjustable lighting so that any of the two astronauts can manipulate it at their comfort. The preferred system for the display is a graphical user interface, GUI, given that it is considered to be more user-friendly than linear programming. Additionally, the display has the capacity to show images from the MASCAM-C.
The Bayrat Systems 5545 multi-core processor is a highly integrated solution with an order of magnitude leap in performance for emerging onboard processing applications. Two boards have been integrated into a rover to guarantee effectiveness and success in case of mishappenings. These two boards will run in parallel, but only one will be processing the data at a time. All of these data processes will also be ran via TMR, meaning that all processes will be performed by three systems producing a single output.
Incorporating sensors in the rover is important to ensure optimal operation and reliability. One of the main sensors selected is fiber optic sensing. This technology is based on the fiber Bragg rating, which is an optical sensor that behaves as mirrors to reflect on a specific wavelength. Using the Summit interrogator by Sensoron, the reflected wavelength will be converted into measurements of strain and temperature. These fibers will be placed in the rover's frame to monitor its structural health and the temperature changes it will experience during the mission. On the other hand, the LN200S IMU by Northrop Grumman will serve as the main inertial measuring unit. This unit will be located in the bottom center of the rover. Since the surface of the moon is not even, this will monitor the orientation of the rover so that its components, such as the robotic arms, can adjust to it. Each robotic arm will count with two interrogated IMUs, one at the base and the other at their respective endpoints. In the case of the core drilling device, the IMU will help detect specifically when the drill will start to go through the surface of the moon by detecting a change in velocity. It will also monitor its angle and position to determine when the drill has gone a certain depth.
Electrical power is generated using a photovoltaic array. The array is made of triple junction gallium arsenide PV cells, which have an efficiency of 32%. The array has solar tracking capabilities in order to maintain a low angle of incidence with the incoming solar rays, and has a total surface area of 4.6 meters squared. Energy is stored using lithium-ion cells. There are 16 cells in total for 3,920 watt-hours of energy storage. This is enough for 1 hour of full electrical load operation at 80% depth of discharge. The vehicle will utilize brushless DC motors as its main drive units. Brushless DC technology was chosen over traditional brush DC technology to avoid the issue of having to replace worn-out brushes during the lifetime of the vehicle. There is one motor per wheel. Each motor has a power output of 400 watts for a total of 1,600 watts. Kapton insulated wiring is used throughout the vehicle due to its high radiation resistance, up to 5 billion rads, and its wide temperature operating range. Goes from negative 269 degrees Celsius to 400 degrees Celsius. The total mass for the wiring throughout the vehicle is 2.4 kilograms.
For the electronic radiation shielding, the solar protons were the only ones taken in consideration. 1 millimeter thick aluminum shielding will be used to meet the total ionizing requirements and to mitigate internal electrostatic discharges. This kind of protection can reduce the ionization up to 80% of the total received for electronic components. The communication systems works with Ka-band satellite communications. One traveling wave tube will be used as an amplifier. This model design has been developed as a high-power microwave amplifier for high-rate transmissions of data and video signals from this space to Earth. High-gain gimbal antennas send the information. The swivel mount allows it to rotate and move directly to antennas on Earth. These instruments will give the rover the ability to communicate with other surface assets, the gateway, and Earth.
Subjects taken into consideration of the development of the cost of EMPRESS were contractor labor, civil servant labor, travel, testing, instruments, and materials. The cost of certain instruments have been based on similar but different systems. Additionally, the cost of the vehicle integration was not included in this analysis. This means that the actual cost of the mission will be higher. This number includes all 4 versions of the vehicle: flight unit, training unit for Johnson Space Center, test unit for Johnson Space Center, and test unit for Marshall Space Flight Center for lander integration purposes. Calculating the different aspects of the vehicle give us a total of $215 million, which represents 1% of the NASA budget for 2020, which is a total of $22 billion.
The different possibilities of risk the rover could have were evaluated according to their likelihood and consequence with respect to the health of the vehicle and the continuation of operations. The 5x5 risk matrix shows the final assessment of these issues. It should be noted that these risks are controlled and mitigated by the systems and the design that have been chosen for this vehicle. The redundancies built in the system of the vehicle provide fault tolerances that enable the continuation of the mission even in cases where critical components such as the motors become non-functional. Additionally, the contingencies taken into the planning of the lunar surface operations, such as considering sunlight availability and surface slope, help reduce these risks.
The innovations presented here show the feasibility of this project, even with the challenges that it could encounter in a real-life scenario. The 5 proven instruments, advanced materials, multiple vehicle configurations, and lunar dust protection systems will enable the rover to carry out its proposed missions. Additionally, the implementation of the fiber optic sensor systems and the IT EMCCD improve the capabilities of this vehicle. Moreover, the ergonomic and safety precautions that have been taken will enhance the rover-crew interaction. All of these features will expand the range of surface science in this new era of lunar and planetary exploration. We would like to thank our mentors, families, and friends for their support during these 10 months of work. We also want to thank the NASA RASC-AL team for the opportunity that you have given us to continue supporting the exploration and development of space with the competition's challenging and revolutionary topics. Finally, I would like to thank my teammates for their amazing work and dedication to this project.